So up to this point in the course, we've discussed the idea of calculating certain statistic parameters such as means and standard deviations and even z-statistics to find probabilities of certain events occurring, assuming a normal distribution. But those were all done for populations, and it's very rare to be able to conduct an experiment on a whole population of people. Instead, what's generally done is populations are conducted on samples that hopefully are representative of an entire population. And we did discuss this a little bit prior, but when conducting experiments on samples, there are certain consequences that have to be considered when actually performing your statistics. And so we're going to go over these now. Let's first perform a hypothetical. Suppose we draw a sample of size little n from a population of size big N and calculate the mean of those n numbers. So we have a population of random numbers of a million random numbers, and we draw 10 of those, calculate the mean of those 10 numbers, and then we put that sample of little n back and draw a new sample of size n and repeat. So we have these million numbers, we pull out 10, find a mean, put them back, pull out another 10, find a mean, put them back. And the question is, what does the distribution of those calculated means look like? So the variability of this distribution, which is we'll call the sampling distribution of the mean, depends on your population size and the sample size that you draw. So we're going to define something called the central limit theorem that basically says if your sample size little n is sufficiently large, the sampling distribution of any statistic that you have will be nearly normal. Generally accepted value of this is a sample size of greater than 30. So going back to our previous example, if we have a million random numbers and we pull out this time 30, calculate the mean of those 30 numbers, put them back, and pull out another 30, calculate the means of those numbers and put them back. The distribution of those calculated means will be nearly normal every time, regardless of what the distribution of your actual sample is. And there are other conditions in which case the central limit theorem applies as well. First, your sample distribution is normal, so if that's normal, then your sampling distribution is normal. That the sampling distribution is symmetric about a mean. It's unimodal, which means there's only one peak and there's no outliers between for an n between 15 and 30. So sampling distribution of the mean, that's what we're talking about here. So again, let's repost the scenario. We draw all possible samples of size little n from a population of size big N and calculate the mean of what we pulled out. We then replace the sample, redraw, and recalculate. So for the sampling distribution, the mean of the population that we have will be the mean of the sampling distribution. So the means stay the same. However, the standard deviation of the sampling distribution changes. Instead of just being sigma like before, now it's sigma multiplied by this quantity of 1 divided by little n minus 1 divided by big N, and all of that raised to the 1/2 power square rooted. Now, assuming that our population size is much bigger than the sample size we draw, this 1 over big N, 1 over a very large number is close to 0, so this becomes 0 and simplifies to this value right here. So this is now the standard deviation of the sampling distribution. So it's sigma over the square root of n. This has another name that you'll find frequently in statistics. It's called the standard error of the mean. So when somebody's talking about the standard error of the mean, it's the same thing as the standard deviation of the sampling distribution. So if we're looking at sampling distributions over a population or a sample distribution, we would ask first, if we're doing statistics on it and it's a normal distribution, how does it change our z-score? How does it change what we need to do to calculate probabilities and make it a standard normal distribution? So this says numerator, it should be denominator. That's my mistake. But the top doesn't change. It's still the value that you get subtracted from the mean of the sampling distribution, which in this case is just the mean of the population, divided by, instead of just sigma, now it's sigma divided by the square root of n, because the definition of what the standard deviation is for this has now changed from sigma to sigma divided by the square root of n. So this is a graphical representation of what I'm talking about. So the trace in red is what we'll call our sample distribution. So it has a mean of 0 and a standard deviation of about 3. And so that's if we just draw all of our samples and just plot them and how frequently they occur within a population. Now the trace in blue is the sampling distribution. So we have our data set of size big N. We draw out little n values. We calculate the mean, and we put it back into the pile and redraw again. And this is how frequently do certain means occur. And what you'll see is it's generally a much tighter distribution about the mean than the sample distribution. And that comes from the definition that with the sample distribution, the standard deviation is just the standard deviation. With the sampling distribution, the standard deviation is much smaller because now it's divided by the square root of the sample size you have. So it's a much tighter distribution. So we're now going to go over a sampling distribution example to make this hopefully more concrete for you. So the question states that the average adult at rest consumes 555 liters of oxygen per day, with a standard deviation of 25 liters per day. You are planning a full-day space expedition for 50 adults and will bring with you a 28,000 liter tank of oxygen. What is the probability that your team will run out of oxygen, assuming everybody is breathing at rest? So what we're talking about here is a random sample of 50 humans, not humans, from a population of all humans on Earth. So if you have a 28,000 liter tank of oxygen divided by 50 people, that means that in a random sample of 50 people, there will be 560 liters of oxygen per person available in the tank. So the question is, what is the probability that a sample mean with an N of 50 is greater than 560 liters? Because at greater than 560 liters per person, you will have used up all of the oxygen in the tank. So we're talking about a sampling distribution. We're looking at how the sample mean is distributed with an N of 50. So it's very similar to calculating the z statistic as before. We have this value. Our x in this case will be 560, and the mean of our sampling distribution is the just the mean of the population here, which is 555. Oh, and we're, yeah, again, given that the mean of the population is the same as the mean of the sampling distribution, which is 555 liters. So the numerator is 560 minus 555, that's 5. The denominator, we know the standard deviation is 25 liters per day and that our sample size is 50. So it's 25 divided by the square root of 50. And when you do this, you get a z-score of 1.41. Now let's use that z-score to hopefully find the probability that the team will run out of oxygen. So we go back to our z-table, and we had a value of 1.41. So we start at the first column with 1.4, and we need to find a hundredths place for 1.41. So we go 0.00, 0.01, highlight that, go over and down, and it's 0.9207. So in a standard normal distribution, the area under the curve to the left of 1.41 is 0.9207. So that means that 92.1% of population lies to the left of this value. So the probability that the individual volume on a per person basis is greater than 560 would be the flip side of that, right? It would be the population that z is greater than 1.41. So what we would do is we would say it's 1 minus what we calculated, because we want the area to the right, not the area to the left. We find that that's 0.0793, or you have a 7.93% chance of running out of oxygen. So hopefully this gives you an appreciation for what we're talking about, the difference between a sample distribution, which is just the distribution of occurrences that you see, versus sampling distribution, which is the distribution of a specific calculated value, such as a mean.